Today we begin our study of electricity. And one can argue that electricity is the key physics behind high tech. When you think that electricity is not just electricity, but electricity includes magnetism. Watch this magnet here. Rather mysterious. Of course, I have a magnet under the table, and I'm moving that around. But amazing. I mean, before class, I was doing, a few simple magic tricks, like the French drop, makes things disappear. Ooh, magic. Actually, not a single person in this class did that. I heard a little bit of sarcastic, ooh, magic. But no, ooh, magic. But look at this. I mean, this is magic. I mean, what's going on here? Hey, I got a motor. Well, not yet, really. If you haven't played with magnets, magnets are basically an aspect of electricity. That wasn't known for a long time. In fact, the first great unification of the forces of physics, well, not the first, the second. The first unification, people talk about the unification of the forces of physics, and it sounds very mysterious, but it used to be that there were two forces that people thought had nothing to do with each other. One was gravity, it pulls me to the ground, and the other is the motion of the moon and the planets, which up in the heavens. And they weren't realized that they were the same thing, that the moon is actually moving around the Earth, held in place by gravity. That wasn't known. It was Newton who unified those two and realized this is the same force. The thing that holds the moon in place is the same thing that keeps me coming in. It's the fact that it's moving in a circle, so it's constantly falling. But it's both gravity. Electricity and magnetism are the same thing in the sense that I'll show you some electricity, and there's some magnetism, and they really are, we now know, two aspects of the same thing. I'll be talking more about that and how that works. Electricity. This morning, we had an electric power failure. As a result, some of these demos aren't going to work as we turn on switch power to emergency generators. But you know what happens when power goes out. The city basically comes to a halt. You can still get around on mechanical things. Your gasoline automobile runs, but the headlights require electricity. The radio, in fact, automobiles don't really run without internal electricity anymore to make the sparks that make the explosions of the gasoline. But electricity is at the heart of computers. What are computers? They're microscopic little things with little channels where electrons flow, and electric lights and electric everything. And this is only 100 years old, and we only began using electric lights 100 years ago. It may seem like a lot to someone who's only 18 years old. To someone who's 62, 100 years ago doesn't seem like that much. But that was the beginning of high tech. Our most convenient source of energy is electricity. When we send a radio signal, we are actually using electricity because the electricity in the radio transmitter, the moving electrons in the radio transmitter, create an electric wave. And that electric wave is how we transmit information from one place to another, almost exclusively using electricity. An electric wave, microwave is an electric wave, radio wave is an electric wave, light, we now know, is an electric wave, just a higher frequency electric wave. So to understand the high-tech world, there's probably nothing more important to understand than electricity. Most of what we use, an electric motor, our iPods, all this is based on electricity. So let's talk about what it is. It came about historically in a peculiar way. When Faraday was looking at electricity, it was basically parlor tricks. I mean, you have things like this, and you rub things together. Now, sometimes you rub things together when you're walking on a rug. And then you walk and you take a doorknob and you get a little spark. And what's happening there is what was called static electricity. This was the initial type of electricity. It was the only kind that was known. Let me take this off. Rub this on this. This, by the way, is a donation from a little kitten that left it in its will for the good of science. Electricity is really turned off today, isn't it? Let me try this. Oops. When this sort of electric experiments were done, this was an example of what was called static electricity. And there, it's repelling. See if I can stop it. Look at that. I can stop it. They repel each other. Wow, just like magnets, except not as strong. So what's the big deal? When Faraday was doing these kind of experiments and trying to understand this, what was called an electric force, it never looked like it would have a practical application. I mean, so I rubbed this with some, I think it's actually rabbit fur, and I rubbed this with rabbit fur, and something happens to both of them, and who knows what it is. But when I do that, they repel each other. Big deal. It's a curiosity. Now they're attracting each other. Now they're doing nothing. This is, let's see if we have some glass rods here. We don't seem to have any glass rods. Now they're attracting each other. So sometimes the electric forces attract and sometimes they repel. So, but you know, so what's going on? Only a scientist would be interested in that, right? I mean, what do you do with this? Faraday, there's a, I think, apocryphal story about Faraday who showed this to a prime minister of England. And the prime minister said, okay, but what good is it? And according to the story, which is probably not true, Faraday said, sir, I assure you that someday you'll be able to tax it. I love that story. That got the prime minister's interest. But it was a few hundred years before it could be taxed, before it really became practical. It started around 1900, when, a little before that, when better ways of creating electricity were invented. And the first real thing was the electric light bulb. Actually, prior to that, electricity was used for arc lamps. They found if you made a spark, you can get light from a spark. If you made the spark across two materials, one of which was lime, the lime would glow, and you get a very bright light out of it. And so this was used first by the military, of course. They made these lime lights, and it could be used to shine on the enemy. Or if you're sieging a fortification of some sort, and at night you want to know whether you blew a hole in it. Soon after that, it was adapted to use in the theater, where people would come in like this, and there'd be a performer. And it's dark, and they didn't have this light. So what they had was called a limelight, which was one of these things with a reflector. It had the spark, and the spark would be continuous. And you'd get that bright light as the lime glowed, and they would shine it on the performer. It gave rise to our expression being in the limelight. I haven't used limelights for a while, although these are still some of the brightest lights that you can make. Then Edison came up with a way of making it practical. So you can take the limelight, and instead of having it in the theater with careful adjustments in a spot, you could have it in your home. The idea was to take electricity and run it through a wire, and it would make the wire hot. And as the hot wire glows, for reasons that we will be talking about this week and next, as that wire glows, it gives off light. And this was his idea for a practical invention that could be used in the home. I describe it in terms like that. It seems almost ridiculous that this would be a useful thing. But this was the tungsten filament bulb. In a tungsten filament bulb, what you do is you have electricity go in a wire. You surround the wire with a glass bulb, because it turns out if you don't, that the hot wire will react with the oxygen in the air and will basically oxidize and crumble. So you put in here either a vacuum or you put in a gas, such an inert gas, maybe nitrogen or argon gas, some gas that doesn't react with the wire. Then you send electricity through it. And what is sending electricity? Well, they didn't know. But you send electricity through it. Where do you get electricity? You get it from a battery. Batteries are expensive. But it was the only source of electricity. Well, this kind of electricity, but the invention of the battery made electricity something that you could carry around. And you send electricity through this, it gets hot and it glows, gives off light. The whole idea that this will be practical seems amazing to me today. But we still get most of our light from this. Now we have a different kind of light called a fluorescent light. And a typical fluorescent light also sends electricity in. A fluorescent light basically works as a big elongated spark on the inside. Now fluorescent lights are a little bit more subtle than that because they put a coating. The spark, it turns out, emits an invisible kind of light known as ultraviolet light. That's absorbed on the surface, and it makes the surface glow. So the ultraviolet light hits here, makes this glow, and then this emits visible light. But basically, it's a long spark, like the limelight was. We're using electricity for most of our lighting. Not all. You can buy a lantern where you use gasoline to make light, but almost everywhere, even little headlamps. When I was a teenager, I used to go cave exploring, and I had a little chemical lamp on my head, which would burn acetone. What was it? What was the gas? Acetylene. Acetylene, thank you. We'd burn acetylene. Someone here use these things besides me? What did you use it for? Same thing, okay. And these days, everybody just uses electricity. Electricity is so much more convenient. So what is electricity? Okay, well, look, we know what it is. We know that atoms are made out of protons and electrons. We know there's a great force between them. That's why the electron stays in orbit, just like the planets stay in orbit because of the gravitational force. The electrons stay in orbit because of this attraction force. Unlike gravity, though, if you have two electrons, they repel each other. If you have an electron and a proton, they attract each other. If you have two protons, they repel each other. So someone came up with a simple kind of math to describe this. They said, let's assume that the electron has something we'll call the electric charge. Now, they didn't know it was an electron, but they knew that you could make things that would repel, like things would repel. They decided there'd be something called a positive charge and a negative charge. And the properties are that two negative charged things will repel each other, and two positively charged things will repel each other, but a positive and a negative will attract each other. So that was the idea. They didn't know about electrons and protons at the time. Now we do. We know that the thing that was called positive charge is actually a proton. There are other things that have positive charge, but almost everything in our experience that has a positive charge is a proton. The negative charge is an electron. And there's some things that have no charge. One of them is the neutron. Inside the nucleus, there are these neutrons. They exert essentially no force on an electron or on a proton. Well, if they get really close, they will exert a force on the proton from the nuclear force. It's a different kind of force. The neutron does experience the nuclear force. It has gravity. It just doesn't have an electric force. So what is an electric charge? Deep down, what is it? Well, that's a question that has no answer. Try to imagine what kind of answer you would like. Some people want to explain this in terms of little mechanical things because they feel mechanical things are things I understand. And so if they could explain this in terms of mechanical things, but it turns out to be the other way around. Mechanical things can mostly be understood in terms of electricity. Electricity is one of those things that's so fundamental that almost everything, including the atoms, are explained in terms of electricity. So if you think, I don't understand anything unless it's mechanical, you're going to have a hard time with electricity. Because it's, in fact, mechanical things that can be explained in terms of electricity. And here are the fundamental properties. Positive things attract negative things. But like charges repel, whether they're two electrons or two protons. And the force can be measured between these things. You take two protons and you hold them next to each other, and there will be this big force of repulsion, big compared to an electron. And you can measure that. And if you double the distance, the force is one quarter. It's just like gravity. You know, you get two things that are attracting each other from gravity, and you go 10 times as far away, and the force is 1/100th. It's 10 squared, smaller. Same thing of electricity. Whether it's repulsive or attractive, the force is what we call an inverse square. You go 3 times further away, the force is 9 times weaker. So these are the basic properties of the electric force. I can design something that will continuously rub. Still disappointed this hasn't worked better. Sometimes it's just a very damp day, and the electricity tends to be lost. The electrons fly off into the air. And when that happens, there are no electrons left to do. Oh, there's nice repulsion. Stop it. Yep. But suppose what I did is I had something that rubbed continuously. I had a little machine to rub continuously. Then this thing would pick up some charge, and this thing would pick up some charge. They'd be opposite. What's happening is we're rubbing electrons off. These atoms, with a mechanical, some of the electrons stick. Let's say they stick to this. This thing comes up. Now, if it comes up, another property of electrons defines what we mean by a metal. Metals can almost be defined in terms of their electrical properties. It's one of the definitions you can come up with. A metal is something that acts like an electron pipe. When an electron gets to a piece of metal, it can move freely within the metal. It can move freely inside of this thing. That's amazing by itself, but the combination of electrons and metals means wires are possible, which is what enables us to send electricity so conveniently. The way it works in a metal is you have all these atoms, and they have electrons, and the last electron on each atom can move easily from one atom to the next. So if at one end you take an electron off, and at the other end you put an electron there, they'll all jump over one atom. And these electrons can move around. They're actually jumping from atoms to atoms, but for all practical purposes, it's as if they're moving freely within the metal. You put too many of them in the metal, and they start repelling each other. Normally, a metal has a nucleus and the electrons, and so there's no net charge. If you have a positive proton and an electron moving around it, and you come over here with another charge, it'll be repelled from this and attracted to this, and the net effect will be 0. So normally, you won't see an effect, not much of an effect. But if the electrons can move around freely. They can move from one to the other in a metal. So let me get back to where I was. Here I have this experiment where what I'm trying to do is I have something that rubs against this. It gets some charge from the rubbing. I bring it up here till it touches a piece of metal. Then the electrons can jump to the metal. And I'll put this on top of a big metal sphere. Then this will come down and rub again. Come up to the metal, drop its electrons. If I get this thing going, I can have something that's continuously rubbing, not just once, and putting all of its electrons on the metal. So I have to take a belt that rubs against something like this and then comes in contact with the metal. Oh, look at that. Here we have one. Inside of this, there is a belt. It rubs against something down there, brings the electrons up onto the metal, and then they stay up here. The belt comes down, gets another one, goes on up. So let's see if this works. Put some electrons on it. Now the belt's running, opposite from the direction I thought it was. And so if that's happening, then there should be, sparks. You might think I'm undergoing excruciating pain with these sparks. Actually, I'm not. I've done this demo now for 5 years, and so each spark jumps to a permanently scarred and insensitive part of my hand, and so the pain is actually quite bearable. I wonder if we could turn the lights down just to see these sparks better. They're quite big. I might get bigger ones if I take another piece of metal. Takes a while for it to charge. Oops, takes a while for it to charge up, and then you get that spark. Those of you over there can see this. Some of you heard thunder this morning. It's amazing that people didn't realize that the thunder that lightning is basically a big spark. That was the hypothesis of Benjamin Franklin. He convinced everybody in the world that that's what was going on, a big spark. How does that happen? Well, the mechanism is actually very similar. You have water droplets rubbing up against the air and then moving to a higher part. Every time I put my hand near that thing, I get a little spark. It's actually quite, look at that. Sparks are, this kind of electricity is often described in terms of the voltage. And one of the things I want you to understand is, what does it mean to be volts? So these sparks are probably about 100, 200,000 volts. Okay? 100,000 volts. What does a volt mean? A volt is the energy of the electron. That's what it means. So these electrons, when they come piling off to hit my hand, have an energy. The term is usually called an electron volt. So let me talk about an electron volt. One electron volt is an energy of, and here's a number you don't need to know, 1.6 times 10 to the minus 19th joules. What you need to know is it's pretty tiny. That's pretty good. Nice sparks. And here we have something which is, basically 100,000 volts. Why do I say volts? Volts instead of electron volts, typically if you have a lot of electrons and they all have the same energy, you say this is the volts of the collection of electrons. But each electron has an energy of this. The total energy that you have here depends on how many electrons you have. So in fact, the energy is equal to the number of electrons times the volts. And that'll give you the energy. That'll give it to you in electron volts. You have to multiply by this if you need joules, but you don't need to know that number. You always look it up. Physics students get to know that number because they use it in homework exercises. But I don't see any reason why you have to know that. What you do need to know is it's tiny. Now, how do I get a tiny number into a large number of joules? The answer is you have a lot of electrons. Now, Avogadro's number, which I wrote down here wrong once, 6 times 10 to the 23rd, that's the number of atoms in what's called a mole. For hydrogen, it's 1 gram. For carbon, it's 12 grams. You look up the atomic weight, it's a few grams for most things. And that's how many atoms you have. You take that many atoms and you multiply it by this many joules, and you get a number that's a few joules. See, this is a small number, but you have a lot of them. So if you want a lot of energy, if you want joules-like of energy, then you need a lot of electrons. And that's what we use in these lights, a lot of electrons. Typically an Avogadro's number worth of electrons. So electricity is moving electrons. Let me take this thing. We used to do this with a student. You'd find a student who had nice light hair. When I was a kid, it usually used to be a woman. Long hair. And you put now what happens is some of the electrons will jump on this thing. So this thing gets the electrons, and since it's touching, these get electrons too. And they repel each other. Imagine how much more interesting this was when you had someone with long hair holding their hand on this. And what happens if I put my hand near it to touch these things? It looks like it's grabbing me. Why is that? My hand isn't charged. So why is it going to my hand? It's called an induced charge. Let me show you how this works. My hand is actually a fairly good conductor. Electricity flows through my blood fairly easily. Suppose I have this big thing here that's full of electrons. And I put my hand here, which I'll think of as a piece of metal. It's a joke about physicists always assuming everything is a sphere, because that's the only thing they know how to calculate. So I bring my hand up here to this. Now what happens? There are electrons in here, and there are positive charges. The positive charges are in the atoms. They can't move, but the electrons can move around. The electrons are repelled by these charges. So the electrons move over to one side. We have positive and negative charges everywhere, but the electrons all move over here, or a large number of them move over there, leaving behind positive charges. Now, because they're further away, suppose I have something on here that also has a negative charge on it. It's attracted to the positive charges and repelled by the negative charges, but the negative charges are further away. So as a result, they're pulled to my hand. Let me demonstrate that again. Here we have the hair, really standing up nicely. I have my metal sphere. The metal sphere has electrons in it, but the electrons are being pushed away by those electrons. So you have more electrons over here leaving behind the positive charges. The positive charges then attract the negatively charged hair. Until there's a spark. Not much of a spark. Well, this thing charges up quickly today. It tends to do very well on a dry day. When the electrons leave this thing, these things are no longer repelled by the sphere. They come down. They lose their charge too. So, isn't that amusing? Yeah, but what are you going to do with this thing? Any practical use? Well, someday you'll tax it. This one is cute. Bill, who sets up this demo for me, doesn't like me to do this one. That's because he sweeps up afterwards to clean it up. Little bits of puffed rice. Buy them in your grocery store. They're getting charged and they fly away. My hair. I can feel my hair being pulled. Okay, electricity. What good is it? It's the basis of all high tech. When electrons travel through the metal, they don't go in straight lines. They bang into the atoms, but the electric force pulls them across. So if I have an electric charge down here that's attracting the electron will come, but it doesn't go in a straight line. It bounces from one atom to another. That's called resistance. And the result is, you'll notice it's not going any faster at the bottom than it is at the top. It picks up energy from falling, from being pulled by the electric field, by the electric charge down here. But as it's falling, it bangs into another atom, gives up that energy. Then it starts falling again. Falling, I call it falling. What I mean is it's being attracted by the opposite charge down at the other end in this wire. So here it is coming down, but it's losing its energy. It picks up energy from the attraction and then loses it on this. That's what makes this thing heat up. So this gets hot. That's what makes the electric light bulb work. Let me just draw a little more explicit diagram for the electric light bulb. Electric light bulb basically works like this. You have a piece of metal at the bottom which you screw into, and in the middle here you have another conductor. The rest is not conducting. This is the conductor. The rest is just plastic or glass. So this is all connected together, but it's plastic. It's a wire coming from this. It comes up here, and the wire connects down to this. Now, when you plug this in, it makes contact with the plug. Okay, you screw this in, and here's one electrical contact, And here's the other electrical contact. And the electricity is made to flow from one to the other. Now, electricity has to go in a loop. The reason is, if the electrons don't have any place to go, they'll just start piling up, and pretty soon they'll repel other electrons from coming. So unless the electron is going in a loop, the electron will stop itself. It's like water. And the analogy between this and water is a very good one. If you have a water pipe, you can start filling up your bulb, but pretty soon you won't be able to put any more in it. Yet it's the flow of electricity that you need to heat up the material it's going through. So electricity has to flow in a circle. You'll sometimes see the so-called high tension lines that are they're supported on pieces of glass. They go over you, up in the air, with electricity flowing through them. There has to be a way for that electricity to come back. Down here at the end, you may hook up through your wires of your house an electric light bulb, but then the wire has to come back. And how does it come back? There could be a separate wire, or sometimes the back path is actually just through the ground. Enough electricity flowing through the ground. It works both ways. You could have two wires, or you could have it come back through the ground. But it has to come in a loop. If there is if let's say the wire comes back this way, instead of going through the ground, we have a separate wire. It comes back like this. Electricity is going in a circle. The electrons are losing energy as they go through here, but you don't want them to lose too much. You have to have a metal that doesn't heat up very much. And that's an important issue in designing of electrical power lines, which we'll get to. The trick turns out to be to use very high voltage. And I'll explain why a little bit later. So the electricity travels this way and then comes back this way. Well, why doesn't it jump across? Why does it go all the way to the end and through the light bulb? Why not just come straight across? We have air there. And air does not conduct electricity very well. So it goes along the wire instead of coming back the other way. Again, imagine it like water pipes. So these water pipes going here. In the end, the water pipe goes through something. It maybe turns a windmill, or windmill, it wouldn't turn a windmill, but turns a mill of some sort, does some work, and then comes back. But if the water had a way of breaking across, it wouldn't go through this resistance. It would come right back. Now, if a bird is sitting on this thing, it's a bird, sitting on the wire, what's going to happen? Some electrons will flow into that bird. And the bird will come charged up, just like some electrons flow on here, just a little bit. Pretty soon, there are some electrons on that bird, and when that happens, they repel additional electrons, so no more electrons go, and the electricity continues to flow this way. They can't go up into the bird because the bird doesn't complete the circuit. There's no way to lose those electrons. The bird just picks up the electrons. Likewise, if you could stand on the wire, and you'd be there, and a little bit of electrons, but it just takes a few to come in, and pretty soon they repel the other electrons, and you're safe. However, if the bird happens to go from here to here, put 1 foot on each wire, say we have an ostrich. 1 foot on each wire. Then the electrons come here, and they don't have to stay there and repel the other electrons. They come right across and come back this way. So now there's nothing to impede it. You can get a lot of electrons flowing. That electrons will start heating up the bird. And we could do this at San Quentin even. It used to be done that way. There's a story behind that that's in the text that I don't know if we'll really touch on, about the debate that took place between Nikola Tesla and Edison early in this century. They both believed that electricity was the coming high tech. I mean, there were so many high techs at the beginning of the century. I think that time was perhaps more disruptive than it is than the high tech right now, with the advent of electricity and airplanes and automobiles and gasoline. And radio. This is all happening around the early 1900s. Very, very disruptive time. The technologies were growing very quickly, very rapidly, spreading into many new areas. But electricity has to flow like that in order to keep on flowing. Otherwise, it just stops. You charge this thing up, and it'll charge up to a certain amount, and then it'll stop charging. Because the electrons here will repel. Oh, look at that. The electrons up here will repel the other electrons and keep them from jumping off this rubber belt. So electrons have to flow in circles. Let me show what resistance looks like when you have a lot of electrons. A feature of electricity, which turns out to be very important, is this resistance is very useful in a light bulb because you heat up the wire. But it's very bad in these transmission lines because you don't want to heat up the transmission line. You just want that electricity to flow. So you try to make transmission lines to have as little resistance as possible. There is a development that could truly transform our technology. So far, it has had just a little bit of an impact. And that's called a superconductor. In a superconductor, this would be similar, except it wouldn't lose energy as it's moving. It will keep up its velocity and not change at all. That's what a superconductor is. Something where electrons flow but give no energy at all to this. Now, superconductors, well, there are two ways to get good conductors. First, let me mention, if I want to slow this down, there is a way to do it. Shake it. If I shake it, as this electron is coming down, it's more likely to hit something if these things are shaking. So imagine the following. Imagine you are an electron. And as an electron, there, on the other side of the dance hall, you find a positive charge, something that truly attracts you. And so you are drawn to it. And you're pulled to that. But there's a dance floor here. Now, I'd like you to imagine whether you will get there quicker if it's a fast dance or a slow dance. Imagine it's, swing or something where people are spinning all over the place and dancing. You try to work your way there, and it'll take you a long time. But if it's a slow dance, then you just sort of get there right away. The fact is, resistance is higher when the molecules are moving a lot. When these molecules are bouncing around, it's harder for the electron to get through. And that means that if you cool this thing down so the molecules are not vibrating as much, then the resistance goes down. Some people find that backwards. They think if you heat things up, the electrons move faster. Actually, most of the electron motion is just bouncing. A little bit of drift in the forward direction. So if you cool something down, the resistance goes down. But a remarkable thing happens when you get to very low temperatures, and that is for some metals, the resistance disappears altogether. That's called superconductivity. I cannot explain superconductivity to you based on the physics of electricity. It requires a concept of quantum mechanics. Let me just state what that is, so you'll be exposed to it. And we'll come back to this when we explicitly discuss quantum mechanics later in the semester. For some materials, when you cool them down, there develops what's called an energy gap. An electron can have a very low amount of energy, or it can have an energy which is higher than that by what's called the gap energy, but nothing in between. That's a quantum mechanical effect. We'll be talking a lot about that when we come to quantum mechanics. One of the key elements, there are two key elements to quantum mechanics. One is that electrons behave like waves, and the other is the development of these energy gaps. Now, the fact that the energy gap develops means the electron, when it bounces into an atom, it can't change its energy unless the energy is equal to the gap energy. As a result, it doesn't lose energy. It just keeps on going. Superconductors, right now, the superconductors we have all require very low temperatures, at least as low as liquid nitrogen, that liquid air that I pour around here. That's a lot colder than in your refrigerators. We have no superconductors that work at room temperature, no superconductors that work even at ordinary refrigerator temperatures. They have to get down very, very cold to work. We understand that for the simple superconductors. We don't truly understand all superconductors. There's something called high-temperature superconductors. I want you to know about these. High-temperature. High temperature means basically liquid air temperature. It's not really high compared to anything you experience in your life, a lot colder than your refrigerator, but it's not as close to absolute zero. Typically 100 degrees above absolute zero instead of 273 above absolute zero, which is the freezing point of water. These so-called high temperature superconductors are not really understood. We don't understand in detail why they have why they develop this energy gap at such relatively high temperatures. If someday we do understand these, maybe then we'll be able to make superconductors that will actually operate at room temperature. That is a revolution. If we start having electricity superconductors that will operate at ordinary living temperatures, you will see a transformation that is enormous in the way we conduct our lives. Everything from light bulbs to electric engines to electric transmission. We'll talk more about that as the class goes on, but I want you to be aware of that. Magnetism was always thought to be something different. Magnetism is also mysterious. It was first discovered in natural rocks. This is what's called a lodestone. It's a piece of rock that is magnetized. Nobody knew what that meant to be magnetized, but here's a needle that's also magnetized. And if I put a magnet near it, let's try this magnet. It repels. That attracts. And this is a big effect compared to electrical. So people got very excited about magnetic forces. If you haven't played with magnets, you should go to a toy store and buy some magnets. I was demonstrating this one for class. This is a magnet going right through the table. Well, my magnet just stuck to something under the table. And we have these magnets that stick to metal. This is such a strong magnet here that it's actually, whoa, these are pretty good magnets too. Ugh. I mean, look at this. Whoa. Force. That magnet there is going crazy. Lodestones were discovered. Whoa. If you've never seen anything like this before, what would you think of it? Right, they're only magnets, right? But to me, magnets are one of the most mysterious things in physics. This force at a distance. You think we'd have some practical use for that. Look at these. They kind of float. Magnetic levitation. Of course, magnetism was a great military secret for a while. The fact that if you took a magnetic lodestone and hung it like this, it would point in the same direction. Eventually, you spin it, it'll wind up pointing in the same direction. Once it settles down, that became the magnetic compass. People didn't know what it pointed at. People said maybe it pointed at the North Star. Well, it doesn't point at the North Star. It turns out that the Earth is a magnet. Magnets are like electricity, except it seems to be more powerful. It's a bigger effect. Real things, I mean, big forces. Magnets are also mysterious. We now know that magnetism is actually an aspect of electricity. It comes about from moving electrons. This is strange, but this is what you need to understand. You have two electrons here, and they will repel each other. But if they're moving, there's a slight attraction. In other words, the repulsion will be less. As they're moving, there's a force that depends on their motion. This is weird. You don't expect the force to depend on the motion. But a moving electron will develop, there'll be this additional electron force that we call the magnetic force. If they're moving fast enough, the faster they go, the more the force is. As they get up to near the speed of light, the force of attraction from their motion is as strong as the force of repulsion. But if they're moving much less than the speed of light, the effect is less. Here I have two wires. I'm going to have electrons move in those two wires. So let me have the electrons move in the same direction in the two wires. And actually, I have quite a few electrons going in here. We have this hooked up to a big battery. And they repel each other. You see that? When I have electricity going the same, they repel each other. It's just the motion of the electrons. The force that comes about from moving electrons, that's only there when they're moving, is actually magnetism. That's what magnetism is. It's a different aspect of the electric force. Permanent magnets like this, there are no electrons moving in this. It's just sort of sitting there. Why should this have... Why are there forces with these things when the electrons aren't moving? Turns out the electrons are moving in this thing. Well, of course, they're moving in the atom. But the part of the electron motion that gives rise to what we call permanent magnetism is from the discovery that every electron is spinning. Every electron moves in it. Well, it stays in the same place, but it spins. And so the electric charge is moving in a circle. And that makes for this magnetic force. So typically in most materials, the electrons are all spinning, but they're spinning in random directions. Up here, this electron may be going this way, this one may be going this way, this one may be going this way, and so on, and it all cancels out. But when you have a permanent magnet, what you do is you take all those electrons and you all line them up so they're all spinning in the same way, so the magnetism adds up. And that's what a permanent magnet is. From electron spin. Spin is another one of these truly mysterious things. We know the electron spinning from the old angular momentum. Remember angular momentum? We didn't discuss much about it. But we had that seat here when you're spinning like this and you watch the Olympics and you're going like this and then you bring your hands in, you go faster. That's angular momentum. And when you pull it in, you have to go faster to have the same angular momentum. And the skinny ice skaters get going really fast because they have to pull all their mass in real close to get going so fast. It was sort of fun to watch that. If you're a hunkier ice skater, you can't get going so fast because you can't pull all of your mass into the same line. But the electron is also spinning. We know this because it has this angular momentum, and it can change its angular momentum. The electron is spinning, and that's what gives rise to permanent magnets. But we can also have electrons moving in wires, and that gives rise to magnetism. Here, repelling each other. If I have them going in opposite directions, they attract each other. I could have electrons moving in a circle like this. If they move in a circle, it's almost like an electron spinning, except here it's not the spinning, it's moving in a circle. And that creates magnetism inside of this thing, and I could try that here. So here I have another little magnet, and I'll stick it inside. This thing is called a solenoid. Whenever you wind wires in a circle like that, and look at that. When I have electricity flowing in it, it suddenly makes the magnet go in one direction. Suppose I have the electricity going the opposite. See, the little red tip is always going to your left. Suppose I make the electricity go in the opposite direction. It goes the opposite way. So here are the key things that I want you to know. Magnetism comes about by the motion of electric charge. Static electricity is just when the charges are sitting there. Like charges will repel, opposite charges will attract. If the charges are moving, there's another force. And that force will cause the electrons to attract or repel, depending on whether they're moving in the same direction or the opposite direction. That's the magnetic force. The magnetic force for permanent magnets comes about from electron spin. But a magnetic force can also be made by winding a coil like this. This is a very practical device. I'll show you something next time where you take a coil like this and you use it to open and close your car doors. Seriously. That's how they work. They have a coil of wire. Here's the lock. You can open the door or you can lock the door. I'm getting mechanical motion. Getting mechanical motion by changing electricity. So by using a switch, I can make this thing go one way or the other. And that's the way car doors work. You push a button and you hear a click as your doors lock. Most cars these days have these magnetic switches. You can imagine making a motor out of this. You have some electricity, and if you do this just right and switch it just right, you can make something turn, make a motor. That's actually how motors work. Most electric motors work on magnetism. Here's an example. We have these magnets here. The electric motors in your disk drives, on your old iPods, the ones that had disk drives in them, they would have magnets, permanent magnets, and electricity flowing. Right now there's no electricity flowing, so let me make the electricity flow. I probably have to turn on some power here. Let's see. See if that'll do it. Now we have some power. I do this just right. Turn it on. Oops. I have to get it just right, get it working. I get it just working right. I might be able to get this thing to make a motor. Well, I have to make my timing just right so that what I want is the magnetism that's created here to be repelled by this, so it goes away, and attracted by this one. But when it comes over here, I want to switch the switch, so now it's repelled and attracted to this one. And then switch the electricity, so it's attracted and then repelled. If I do that just right, I have what's called an electric motor. Now, there is a way to make the switching work just right, and that is if I automate it. If I design this thing so the switch happens automatically every time it goes halfway around, then it'll get going faster and faster and faster. So maybe I'll set up one of those for next time where I can get that happening automatically. That's what an electric motor does. An electric motor uses electricity to create a magnetism. It then uses that magnetism, these days often with permanent magnets. But sometimes, instead of having permanent magnets here, what you'll have is another coil. So electric motors are using electricity to make something move, typically in a circle. That's the idea of an electric motor. We're turning electricity into mechanical motion. This thing is now pointing back in the same direction as it was. It's pointing back in that direction because the Earth is a giant magnet. Let me talk about the Earth's magnetism. So here's the Earth. If you have a little magnet like this, the end that points north is sometimes colored blue, as it is here. Sometimes it has a little N on it. The other end has a little south thing on it. It's a magnet, like this. The part that points to the north is called the north pointing end, or often called the north pole of the magnet. Now, magnets, unlike electricity, have a peculiar feature. Remember I pointed out that when I put my hand near that electric source, this thing has a lot of electrons on it, that some of the electrons move over to this side, leaving positive charges behind. There's no net charge on this thing, but the charges have separated. Magnets are all the same way. If I break this magnet in half and take away this part, I still have a north end, and now this thing becomes the south end of the magnet. Magnets are all dual-ended like this. This little charge thing. One will be a north side, the other will be a south side. Here is the rule for magnets. If I take two magnets, if I can get rid of them, and I take two north poles, and they bring them close to each other, they will repel. They repel. If I take two south poles, this is let's try it over here. Two south poles, they likewise will repel. But if I take a north pole and a south pole, they attract. Or a south pole and a north pole, they attract. Very much like charges. Magnets have the same property that north poles, like poles, we call them poles because they point to the North Pole. Here's the pole. This is the North Pole. The Earth is a big magnet. Here's a little bit of irony, and you could have fun with your friends or parents or anybody else you want to tease. The North Pole of the magnet is attracted to this part of the Earth. So what kind of a magnet is that part of the Earth? Well, if the North Pole of your magnet is attracted to it, it must be a south magnetic pole. And down here, there must be a north magnetic pole. And here's your big magnet for the Earth. So the fact that some people, this terminology can get very confusing. You call this the north pointing pole. But in common terminology, it's the North Pole of the magnet. Because it points to the north. If it has a little bit too much friction here, but this one here will point to the North Pole of the Earth. This is the north pointing magnet. It's pointing to the North Pole because the North Pole of the Earth has magnetism that attracts it. By our definition, the magnetism at the North Pole is a south magnetic pole. And the magnetism at the South Pole is a north magnetic pole, so it attracts the south end of the magnet. So no matter where on the Earth you have these things, they tend to point in this direction, unless there's a lot of metal nearby. You take a magnet like this, and it'll point to the North Pole as long as the Earth's magnetism was what dominates. If I happen to have a piece of metal nearby, this thing will point in some anomalous direction, and the magnetic compass will not work. Will not give me the direction that I want, that I need to know. Why is it when you break a magnet, you can't break off the North Pole and just have North Poles? The answer is because a magnet is actually a permanent magnet. It comes from the spin of the electrons. So let me draw that over here. Here I have a piece of metal, typically iron. In iron, you can get the electrons, at least one electron for each atom, all spinning in the same direction. So they're moving in circles. They're spinning like little tops. Let me draw little tops here. They're all lined up like this. Because they're spinning, it's hard to believe that this thing has all this internal spin in it. But when you have these magnets and you have the electrons all spinning in the same direction, deep inside of it, this thing is spinning. The outermost electrons are spinning. Because they're spinning, it's like electricity moving in a circle. And so here we have electricity moving in a circle. And that makes a magnetism on the inside. If I break this in half, it's still a magnet on the inside with the electrons causing the magnetism to go in this direction. You break this in half, and you still have that property that now you still have the electrons spinning like this. This will become the North Pole. This will become the South Pole. That basically means that if you put a magnet, it'll tend to be, suppose I take two of these magnets and put them together like this. These two North Poles will repel each other. But this north pole will be attracted to this south pole. That'll tend to pull them together. This north pole will be attracted to this south pole. That'll tend to put them together. So do these magnets attract or repel? The answer is they will repel because the north poles are closer. And because this thing is further away, therefore the force is weaker. So these behavior of magnets, like here, if I put the north and the south pole against each other, they attract. At the same time, this is repelling this. Watch, see, it repels it. But it's so far away now that the attraction is more important. Okay. Magnetic recording is based on the fact that you can make a piece of metal magnetic by putting another magnet next to it. In your hard disk drive, in your computers, it records signals using magnetism. Let me explain a little bit how that works. Let me use this one. There's a lot of research that's done into finding the best possible magnetic materials. And there's so much money in this business that better magnetic materials are being found all the time. Let's just take a very simple magnetic material such as iron, and we'll make a disk out of a thin piece of iron. In this thin piece of iron, let's look at this thing up close. Here it is. The iron will have the electrons spinning in many different ways. If you want to record a signal on this, things are recorded on these things in terms of signal is either 1 or 0. And you put a lot of 1s or 0s on here using magnetism, and the entire digital signal is made of 1s and 0s. You can encode letters of the alphabet that way, or brightnesses with 1s and 0s. The way this works is they take a coil of wire, send electricity through it, turning this into a magnet. So you're making a magnet by electricity flowing in a wire. That magnet will cause these magnets to be, if this is the south pole, they may be repelled. This is the north pole, it might be attracted. It'll cause these magnets to flip over so that this, when you send the electricity through this, this will turn into the magnets being aligned. So you put the magnet down here, you turn it on, it puts a force on these things, causes them to flip over. So it's like turning on this magnet and making this rotate. The magnets will rotate till they're all pointing in the same direction. Then you remove this magnet. Actually, you don't remove it. What happens is the disk is moving. And as it passes over this magnet, you turn the magnet on. These individual electrons line up. And then they move away from the magnet, and they're left lined up, and they stay that way. If the north pole is down here and the south pole is up here, it'll be one signal. Maybe that'll be a 1. If the south pole is down here and the north pole is up here, if they're spinning in the opposite direction, you can call this a 0. And so this is what a magnetic recording does. Is this the best way to record signals? If you had asked me 20 years ago, I probably would have said no. It's hard to predict the technology that will turn out to be the most practical for recording information. What they've been able to do is to make these regions extremely tiny. And by making them extremely tiny, they can make them so you can store a lot of signals on the disk. And as the disk is spinning, what you could do now is put a wire up here, and you can sense the magnetism of this little region. I haven't talked about that yet, but we'll come to that on Thursday. So as this thing spins around, you can record on it by having a magnet, and then you can read it off with another magnet. As this thing is spinning, every time the disk comes to where your sensor is, you detect whether it's a north or a south pole, and then you know what was stored there. Then you can reset it. You can change this and store new information on it. This is what's happening on a hard disk drive. You have these thin plates of magnetic material. You have wires that create magnetism. And the magnetism is a way of storing information. You know, you're only storing an up or a down. You're storing a north or a south pole. That's it. But the amazing thing is, if you store ones and zeros, you could let, for example, every 3 letters, 110 versus 111. This could be a code. This could indicate the letter A. This could indicate the letter B. And the pattern that you leave there could lead to that information. Or you could have this, these could be numbers that represent the strength of a field, the strength of the sound, for example, the loudness of the sound. And then you're recording music. So this is what happens with magnetic recording. What do I want to cover in the last 5 minutes? Let me talk about transformers. I said that this thing becomes a magnet when we have electricity flowing through it. Let me use a little bit of relativity theory. Relativity is something we're going to get to more and more as the semester goes on. And one question is, where does the term come from, relativity? You'll see that in a moment. Suppose I have electrons flowing through a wire. That creates magnetism around that wire. That magnetism can exert a force on another magnet. An electron, see, I don't want to say this. Let me introduce the concept of a field. We've come across this before with gravity. It makes more sense, or it becomes more important to think about for electricity, that when you have electrons here, how do they exert a force on another electron? There's no mechanical linkage, or is there? Force at a distance, where does that really come from? It's a very abstract motion, and it's hard to really know. But the following approach, it turns out, makes some predictions that are verified. And so this is now the standard way of thinking about it. An electron, when it's just sitting in one place, creates around it, it changes the space around it. It fills that space around it with something that we call an electric field. The electric field gets weaker as you get further away from it. Gravity does the same thing. You say, here's the Earth, and the gravity has a gravitational field. The way you could tell that there's a field here is if you put an electron right here, another electron, that the field exerts a force on the electron. An old way of looking at it is you say an electron exerts a force on an electron at a distance. But we've been driven to believe that that's not the way it works, that the electron creates a field. A field is just a name for an alteration of space, such that this space over here has a property that if you put an electron, that it'll be pushed in that way. I tend to think of a field as filling up of space with some kind of an energy that can exert forces on other electric charges. This same field on a proton would pull the proton this way. On a neutron, the neutron doesn't sense the field at all. Some people think of a field as it's similar to a stretched piece of rubber. This electron is distorting the space out here in some way. The reason that we're forced to come up with this notion is because if you put the electron here and it's repelled, and you have an electron here, and it's sitting here creating the field, and this electron is being repelled. Suppose you suddenly take this electron and remove it. Does the force here go away instantly? The answer turns out to be no. The reason is if you remove this instantly, the field doesn't change right away. The field is still there. It's a property of the space, and once this electron is gone, the field will begin to disappear, but the disappearance of the field only goes with a certain speed. The speed for the collapse of that field, think of it as if you have a big stretched rubber membrane, and you're holding down something here, and it makes the whole rubber membrane tilt, so something here will start rolling towards it. But if you remove your fist suddenly, does the rubber membrane spring right back right away? It takes a little while. You put an electron in space and suddenly remove it, the electric field doesn't disappear. It first disappears over here, and then it spreads. The disappearance spreads with time. It moves with a certain velocity. That velocity turns out to be the speed of light. The field does exist even when the electron's not there. In fact, if you take an electron and shake it, you can shake that field. It's called the electric field. That shaking electric field becomes what we call an electric wave. An electric wave is a microwave, it's radar, it is visible light.